Hey everyone, what we're going to do in this video is talk about statistics that are generally geared towards clinical diagnostic type studies. And so we've kind of labeled this as clinical block 1, but mostly we're going to talk about prevalence, sensitivity, specificity, ROC curves, and just some other ratios that go with those. So really what we're talking about is sort of a test to real world characteristic. So we're looking at how tests are either valid or they're not. So let's say we have a test for a specific disease and we really want to know what's the prevalence of that disease because that will influence the results of our test and the characteristics of that test. And then we can also look at the predictiveness of that test. So we're going to start with kind of this square here of the truth. Somehow we know the truth, the real world, and the test result. And so the test can either be positive or negative. And so the easiest thing to think about here is either pregnancy or HIV. Those are the two big examples that these sorts of things work for. But any kind of cancer test, any kind of test that either gives you a positive or negative result. We'll talk in a little bit about tests that give you more continuous results. But I'll say it's either a positive or negative result. You either have the disease or you don't have the disease. And I'm not calling pregnancy a disease. So you either have the thing or you don't have the thing. What that means is that this ends up being like kind of like I always think about this as a giant game of Battleship. So when you have a positive test and you have the disease, that's a true positive. So that tends to be sometimes considered the hit rate. So it means that you have found the thing that you're looking for. In statistical terms, it also is kind of similar to power. So the test is positive and we're supposed to have found a positive. Okay. If the test is negative and you were supposed to have found it, it's called a false negative. So you missed it. If the test is positive, but you don't have the disease, that's a false positive. So this is kind of like type 1 error. It's saying something happened and it didn't. And so this is bad. This is telling someone they have a disease and they don't. Then a test that is negative and should be negative is a true negative. So this is also a hit. We've correctly classified them as not having the disease. So this diagonal here is good. These are things that we want to have happen. So we would want the most people in those boxes because we correctly classify the disease and then we correctly classify not having the disease. These off diagonals here are bad, meaning that we missed it and they have the disease and they're not getting treated, or we're saying they have the disease and they're getting treatment they don't need. So both of these things here are bad and we want the numbers to be small. And then we can add up and get how many times a positive test happens, how many times a negative test happens, how many people have the disease, how many people don't have the disease. So in this case, that's why I wrote as the truth, because sometimes you won't know it's a false negative at first. So a good test has most of the areas here in blue, and most of the areas in red are low. All right, so let's start with prevalence. So prevalence is how likely the disease is. And so it's the total here in the disease column. So the total number of diseased people or whatever divided by the total number of people in the study. And we can make that into a percent by multiplying by 100. You'll see these kind of presented either as all percents or sometimes all proportions. And so prevalence, the problem with prevalence is that it's heavily influenced by the population you use. So one of the problems they originally had with HIV predicting prevalence was that they thought it was only seen in the LGBT community, especially in gay men. And so the population they were using influenced those numbers. Whereas we know now, we know better. But the group of people that you study will influence these numbers because if you manage to get a sample that didn't have a whole bunch of the disease, but that's because of just the group of people you picked, then you missed all those other people. So the sample itself influences prevalence numbers, and that's why they're usually an estimate. Often because we don't know they're false negatives out here, or we've missed out on some of these other scenarios. But where was I going with that? So sometimes you just don't know the truth, and sometimes the sample is bad. That's what I'm trying to say. Sensitivity of a test. Okay, so now getting into the test characteristics and not the population characteristics. So, given the sample, the sensitivity of the test is the probability that that test will indicate disease among people with the disease. So it's the probability of getting a hit. So saying that they have the disease and they do have the disease and the test came out that way, divided by the total number of people that actually have the disease. And this is just like how many times you got it right for just the people with the disease. So how sensitive are you at detecting that disease? Whereas specificity is sort of the opposite of that, but for negatives. So it's the hits for negatives. So sensitivity and specificity are both hits. It's how many times you find what you're looking for and you're right. And so specificity is how many times you find true negatives out of people who don't have the disease. Okay. So we don't really have rates for these. We just take the subtraction. Because these are probabilities, they add up to 1 or 100%. So the true positive rate or sensitivity is to get false negatives, you just do 1 minus sensitivity, or if you do percents, 100 minus sensitivity. The specificity, again, is the likelihood of finding the negatives that are true negatives. So it's true negative divided by total non-diseased, and then if you want percents times 100. So sensitivity and specificity are characteristics of the test. The population prevalence will influence those, influence the numbers you get here, but this is it's about the test itself and not about the population. So we want really high sensitivity and specificity numbers because think about it, they're measuring the hits. So the lower the number, the more you're missing it. Okay, or you're unfortunately giving people false positives. Now, we can also convert by going across here and talk about positive predictive values and negative predictive values. So positive predictive values are more, I think this is more like what people want to hear in the office. I want to know before you give me the test that it is a sensitive test, it's going to find the disease if it's there, and it's a specific test. So it's going to tell me that it doesn't have the disease when it's not there. So that's the characteristics I want to know before you give me this expensive test. But then when I get my results back, I want to know how much I can believe those results. So what is the chance that a person with a positive test really is positive? So sensitivity is the likelihood of finding positives when they're really diseased. But now we're talking about what's the likelihood, if the test is positive, of actually having the disease. So it's kind of two sides to a coin. They're not opposites of each other, but it's two different focuses. One is about, I already know you have the disease. How likely am I to find it? The other one is, I know you have a positive test. How likely should I believe it? And these are questions that I think it's easy to get confused, but because generally we're on this end, where I know what the test result is, but I don't necessarily know the truth yet. So this is why they'll have people get tested, maybe several different ways or several times, is making sure that positive result really puts them in this true positive category. Okay. So positive predictive values are the true positive results divided by the total number of positive tests. And I've seen and said the word positive so many times it doesn't look like it's spelled correctly anymore. Let's talk about negative predictive values is the hit the other way. So it's the true negative results divided by the total number of negatives. So we want both of these numbers to be high too. However, those are influenced by the prevalence of the disease. So sensitivity and specificity are about the test itself, but the positive predictive values and negative predictive values are really influenced by prevalence in that population. Because the change in prevalence will really change these numbers. And we'll do an example here and then you'll see that. So actually let's try that example now. So let's say that we have a disease that we got 10 hits for true positives and 40 false positives. So that's really bad. this is going to be a particularly poor test because we got 10 correct and 40 we told had a disease, but they don't. So we have 50 positive tests. We also have 50 negative tests, but only 5 false negatives and 45 true negatives. So this column's good, but this positive thing is not so good. The prevalence of the disease is going to be 15 out of 100. So the total number of diseased divided by the total. So that's a low prevalence disease in this specific example. The sensitivity of the test is 10 divided by 15. So it is the number of true positives to the number of total diseases here. So 10 out of 15 is 67%. Check on my little phone calculator here. Right. The specificity is 45 out of 85. So the number of true negatives to the total number of people with non-disease. So this is not as good. Okay, and that's 53%. So if I get a negative, if I'm in the non-disease category, so I don't have the illness, there's a lot of false positives going on here. So it's only a 50-50 chance that this true negative is accurate. Positive predictive value is 10 over 50 here, which is 20%. So if I get a positive test, it's only 20% likely that that's actually true, which is bad. And the negative predictive value is 45 divided by 50. Okay, so 90%. So if I get a negative test, it's probably pretty likely. If I get that positive test, all bets are off. So what I'm going to do here is I'm going to change this example. I found this example online. I thought it was a really good one. To just change really the prevalence. So we've changed the likelihood of the disease. So we shifted the disease from 15 to 85, oops, wrong way, sorry, to 30 to 70. So kind of keeping sensitivity and specificity the same, but we're changing the prevalence of the disease. Okay, so prevalence is still 30 out of 100 here, or is now 30 out of 100, which is 30%, versus 15% before. Sensitivity is 20 out of 30, so we're 20 here out of 30 here, which is the same rate of 67%. Specificity here, our true negatives, is the same rate, so 37 out of 70 is our sort of 50-50 rate. Right, so 53. So it's 50-50 if you look at these two numbers. Now, what does that change? So we've upped the prevalence of the disease, and we've left sensitivity and specificity alone. How does that affect positive predictive value? So now it's 20 out of 53. And so that increases our positive predictive value from 20% before to 38% now. And so there's just more disease, so you're more likely, more positive test is more likely to be true. Right? So this is, I guess, kind of like the flu. I don't remember the prevalence rates for the flu, but I would assume that disease is a lot more common, right? I shouldn't call it disease, that condition. And so finding a positive test when there's more positive tests to be had is more likely. So if everyone around me has the flu and the prevalence is high, I'm going to take that positive test as to be pretty accurate. Now, 38% is still not a good number, but it's more likely. The negative predictive value is 78%. So these are going to kind of vacillate with each other a little bit. So this one has actually gone down because there is more disease to find. Okay. So higher prevalence increases positive predictive value, especially when you hold sensitivity and specificity constant, and it sort of decreases negative predictive value. To go along with this concept, we're going to do a couple of things. One of them is likelihood ratios. So likelihood ratios are all about people with the disorder versus people without the disorder. So you got to keep that part straight. So it's the likelihood of a test result. So this is the likelihood of people with the disorder to people without the disorder. So a likelihood positive ratio is sensitivity divided by 1 minus specificity. And so that is the likelihood of getting a positive test with the disorder to without the disorder. We want these numbers to be high because if I have this stupid disorder, I want the test to be positive so I can get treated. And so the likelihood of finding a positive test when I have the disorder to without should be a high number. And so likelihood ratios range, but 1 to 1 means you have a 50-50 shot. So we would want these numbers to be greater than 1 because that means I have a higher likelihood than chance, 50-50 being chance, to find the positive test when I need it. A likelihood ratio for negatives, so this is like getting a negative result on the test, is 1 minus sensitivity divided by specificity. And we want those numbers to be low because if I have the disorder, I want to know I have it. And so getting a negative test is bad. And so we want these numbers to be close to 0, meaning that the likelihood of me getting a negative test when I should get a positive test is very low. So you can also weigh those by prevalence. So I can take those ratios and weigh them by the likelihood of the disease overall and see what the ratios are in that case. All of that, thankfully, can be done online. And so you can use VassarStats websites, and it'll actually give you confidence intervals as well. So let's go try those examples on their website. And you can click directly on this link to get to the Clinical 1 calculator. Or if you go to their overall website, hey, there it goes. Click Clinical Research Calculators, and it's the first one. And so we could enter all the numbers we just tried here with the warning that when I made all of my graphs before I looked at this, I did present and absent because that's generally how you see it presented. So make sure you're entering them in the right order because they have absent first. So let's go back over here and do example 1. So they have a positive test and present 10 to 40. Okay, so positive test and present, so it's 10 over here, 40 over here. And then 45 are a negative test, and I should have said present, it's 5 to 45, but that's just backwards from here. So watch the order of the charts. Okay, that's all you have to do. So you hit calculate, you make sure all of your numbers add up, and you make sure you've done it in the right order, because I did it earlier and was like, well, I can't math. And it gives you all of the numbers that we just calculated by hand. So prevalence is 15% in this first example, but it also gives me a confidence interval for those percentages. So we talked throughout the semester about point estimates. So the mean is a point estimate, a regression coefficient. So that's one number representing all of the data. And confidence intervals are just a better way of representing. So yeah, the prevalence is 15%, but given our sample size, here's a range that might actually be a little more accurate. So it might actually be somewhere between 9 and 24%. And so that gives me a kind of a range of numbers that I might expect. Shows me sensitivity and specificity. This set of numbers here is just the totals divided. So the likelihood the test is coming out positive or negative. We're more interested in positive predictive values. It's only 20%. That's no good. The converse of that is false positives. So these add up to 1. And then negative predictive values. So this is really good. When the test is negative, we're pretty sure that that actually means it's negative. When the test is positive here, we're probably pretty sure it's actually false positive. The other thing you get here is those likelihood ratios. So they have the conventional ones, which is the likelihood. Let's go back. I find the wording on this very tricky. Oops. It's the likelihood of sensitivity to 1 minus specificity. So when I get a positive test, it shows me that I do have the disorder. So over 1 is a good number here, even though the true positive predictive value is pretty low, right? The sensitivity and specificity of the test helps us out a little bit. And so if I get a positive test, I am more likely to be positive than not. But this negative number should be much lower, right? So if I get a negative test, I want this to be very low, because a negative test implies that the person with the disorder to without the target disorder, I want the likelihood of me getting a negative test when I have the disorder to be really small. Now, if I weight those by prevalence, you can see that this test is just not very good, right? Because they're both very small numbers. So it's good for, it's not very good at all, because I want this one to be large and I want this one to be small. So it's good for the negative end, but not so much for the positive end. All right, so though all of that is about the test itself and the prevalence of the test, so our prevalence of the disease. So these two things kind of can work together, right? So if I have a very infrequent disease, it's going to be hard, even if the test is very sensitive, it's still going to be difficult, right? But if I have a very prevalent disease and very sensitive and specific test, it's going to be much easier. Okay. The other kind of last piece that weaves into this are receiver operator characteristics, or ROC curves. Okay. So it's an extension of sensitivity and specificity. So how likely I am to get a hit. So true positives and true negatives. And so it takes that true positive rate and plots it as a function of the false positive rate, or 1 minus specificity, for these different criterions. So we're calculating the rates of true positives to false positives, and creating a picture of what that looks like. Now, I say this is for non-binary categories because to be able to do this, you don't just have positive tests and negative tests. You end up having different positive and negative tests at different criterion levels. Okay. So each point on that curve represents a sensitivity specificity pair to a particular decision threshold. So the example I saw online was about thyroids. So different levels of the thyroid, oh man, it's got a name. I've lost it. Chemical hormone stuff in your body, and rating tests on problems with your thyroid. Right? So the area under the curve, so it like each of those thyroid levels, they were predicting, if the person had needed treatment for their thyroid. So it wasn't a simple yes or no. So it's not like, do I have cancer or not? It was at each level of this test, what did we need to do? And so we have more than just a yes-no binary. We have a set of pairs with sensitivity and specificity. So the area under that curve tells me how well that test can determine between a diseased person and a normal person, or I need treatment and I don't need treatment. So I think it's much easier with a picture. And I just pulled two of these offline. So we've got false positive rate on the bottom, or 1 minus specificity, sensitivity on the y-axis, or true positive rates. A dashed line here means that the test is 50-50. You have no effing idea. Okay. As it moves toward the sensitivity section, your test is getting better and better at diagnosing people who have the disease. If your test actually curves downwards, that means you're actually you're getting it more wrong than anything else. So we want curves to always be above the diagonal. That means they're getting better. Now, some people will plot the negative rates, which the curve should be on the bottom, but most of the time you see these as curves on the top. And so the area under the curve is sort of a different metric for how good the test is. So the larger the area under the curve, so here for the orange, the more you're getting it right. So the better the test is. Now, VassarStats also has a picture for this that you can use. So I'm going to click on Clinical Research Calculators, and then go down here to Simple ROC Curve Analysis. Now the problem is that their picture isn't working. So here's a stupid thing. T4, that's what it was. So they had the example of thyroids. And so looking at false positive rates and true positive rates for thyroids, and we don't have any of the negative tests here. So this is only when the test is positive at the moment across different diagnostic criteria levels. And so you would need a test that has more than 2. Right? That's the whole point here, is that it's not just positive and negative. It's how many times a positive comes up based on these different levels of whatever you're interested in. Okay. And so it will graph for you. So what you do to get the information here is you enter the number of false positives and true positives across the diagnostic criteria here. So let's just make some up. So let's say we get 4, 3, 5, and at the top we're only missing a couple people, and we get a whole bunch of true positives. Oops, I'm not very good at making up random numbers. And I would hit calculate. So we'd enter false positives and true positives. Calculate. And normally it'll make you a graph right here, but alas, I do not know what is happening with set graph, but it is not graphing. It gives me this crap right here. So we're going to come down here and we're going to look at it. So the number of actually negative cases, 13, is just the addition over here. Okay. Number of actual positive cases, 180. That's just the total here. It gives me the fitted curve. So this is the logarithmic fit. So this is nonlinear. So we're not fitting a straight line to this. We're fitting a curve to it. So it's a log curve. It tells me the area, the r-squared value, so how good the fit is. So you want very, very big numbers here. And it gives me the area under the curve. So that's not so good. We would want that number to be much, much larger. And what we can do to make that picture is copy down there predicted statistics here. And I created a little Excel sheet where I can paste my data from VassarStats into Excel, and it will auto-calculate or auto-create you a picture of that data. And so this gives us that curve, and it's not very good. So the area under the curve is only 30% here, which means in a perfect world, we would have a straight line through here. So we're actually kind of below 50-50 chance with the numbers that I just made up. Okay? And so it'll calculate the false positive rate to the true positive rate and create your picture. And another thing we can do is add the 1-to-1 line on here as well, which I can do right now. Or you know what? Let's actually just make it even easier. We'll just draw it on. So let's see here. Shapes. So this is how we know we're not doing well. This will be the 1-to-1 line. Given this picture. So we're doing pretty poor. We're actually below a perfect prediction. And so that is how I'd create that picture, because it doesn't show up on here. Maybe by the time that you guys get to this video, it'll magically reappear. But I created this Excel sheet so you could plot those and make it look nice and pretty for reports. So all that together is about the diagnostic criteria of a test, and how sensitive and specific the test can be, as well as how predictive the numbers that you get from the test are. The second clinical block covers risk and risk ratios and odds ratios of different experiments that will try to reduce the amounts of disease.